So what we're going to talk about first is the physiology part. Like, how does a nerve fire? What is a nerve impulse? When you hit your funny bone, have you hit your funny bone before? You know, it shoots down to the pinky. What is actually happening? What's that physiological functioning? And then we're going to have a second part where we look at the microanatomy. It's like, how does a neuron, look at that, how does a neuron look? And then we'll finish that up. And then on Wednesday we look at the big stuff. We'll start with that. So the nervous system works on electricity. And electricity is what we use to send nerve impulses through these channels here, through these cables, where you can see here, up and down here, that's a backbone kind of depiction, and then that's the brain, and so the electricity runs through all these nerves and go through all the body cells that we have. And electricity works on the law that opposites attract and likes repel, so we talk a little bit about that. And then we get into charged fields and voltage, and that's where it gets a little bit tricky. And then we work that way up into the action potential, which is a nerve impulse. And we'll see where we go with that. The nervous system connects us to the external and the internal environment. So the nervous system is a communication system. It's a system that lets the brain know what's going on everywhere in the body, and that way it can coordinate function. You can coordinate growth when we're made, but then it coordinates function once we're made. So it controls and coordinates every function in the body. When it says external environment, that means you're looking around, you can see what's going on out here. When we say internal environment, that means the nervous system knows how fast your heart's beating, how fast you're breathing, all that stuff. It knows all that. It's made of a computer, so to speak, and a lot of cables. And a computer is the brain and the spinal cord, the brain and the spinal cord. And the cables is what comes out on the side of the spinal cord and then feeds to all the body cells. Brain and spinal cord together, we call those two the central nervous system, CNS. Central nervous system, as compared to the cables, we call that the peripheral nervous system, because those are the cables on the periphery, on the outside of the center. So the core is the center. And when we look at basic functioning of how nerves function, we go back to the negative feedback loop. Remember the negative feedback loop where it's too hot? We pick that up. The body needs to cool things down to bring it back to a center, to a balance. So the fact that it goes to a balance, that means it's a negative feedback. So here is the same components. We got a receptor that detects a change and sends a sensory impulse to the brain or the spinal cord. So here we got a receptor. The receptor's in the skin. We poke the skin. It hurts, but we don't know that yet, because that impulse needs to be sent to the spinal cord here and then up the brain for interpretation or integration of the information. And then once we know what's happening, once we realize we got poked, and the brain realizes that, we're gonna pull the finger away. And we do that because the brain sends an impulse, an effector impulse, or an efferent impulse, to a effector, and here that's a muscle that pulls the finger away. The effector can be a muscle, but also a gland, and definitely another nerve, the recipient of the message. So that's important because that tells us that nerves only communicate and connect to other nerves, to muscles, or to glands. To me, that explains when people have a lot of anxiety in the head, a lot of energy in the head, they need to move to calm down, they need to talk to calm down, or sometimes they start having smelly pits when they have a lot of anxiety, and that's the glands, or the sweating. Yeah, well, that's how we work, huh? So, fundamentally, we have a brain and a spinal cord that integrate information, that coordinate things, and then we got nerves on the side, the peripheral nerves, that bring the information to and from the body. So it's a two-way street. The impulses that send it from the receptor into the cord, we call them sensory. The impulses that go from the cord back out to the organs to make a change, we call them motor. Here's the word motor. That's the difference between sensory and motor. We'll get a lot of that coming in this chapter. Might as well start with those terms. Yeah, now we get to this electricity. Electricity runs the nervous system. So electricity is the energy that sends the message along the cables. That's what the electricity does. Nervous tissue needs to be able to respond to electricity, so it's very reactive, and it needs to be stimulated to respond to something. That reactivity term, we also call that excitability or irritability or responsiveness. Those are terms that mean the same thing. The cables that the electrical impulses go through are wire-like extensions from their cells. They're basically parts of a cell. So a nerve, and a neuron, is a cell that has a part that's a body, that's like the thing that we learned about the cell, that has all those organelles and all that stuff. But then that cell has extensions coming off of it, and has like finger-like things that reach out. And those are great because those give us places where other extensions can come to and connect to it and have a conversation with them and stuff, so forth. We talked about the muscle, where the nerve comes onto the muscle and then the acetylcholine goes and reacts to the muscle. Similar stuff can happen here, just from nerve to nerve. And then a nerve from a cell body place has one long extension that goes all the way from that part of the body to wherever that nerve needs to go to communicate with. That can be a muscle. That would be where the muscle attaches. That's the neuromuscular junction. That would be something like that. That also could be another nerve, or that can be that other gland. But very often, for example, we have a nerve that sits up here in the head, in the brain, and the extension, the nerve cell body, and the extension goes all the way down the spinal cord to the place where the nerve then comes out. So that could be a long extension, up to 1 meter long. And that's the part that the electricity is sent through. That's that wire-like extension. We're going to term that, it's going to be the axon. But we're going to learn about that in the second half of the lecture today. So when we look at electricity, what is electricity? Electricity is the flow of positive and negative charges. This here is a picture of a tube-like structure. That's one of these cell extension things. And here you see right on the inside you have positives, and then on the outside here you have negatives. That was, a little bit. So here you got the negatives and the positives. And then the flow of electricity is the flow of those ions or the charged molecules. Here in the body, they are the ions. Remember ionic bonds? They're charged molecules. They're either positive molecules or negatives. But on those molecules, you have a charge on it. And movement of that charge is the electricity. So changing the inside from positive to negative, moving ions around that are bringing negative to the inside of this cell, that makes the electricity. That change in that charge from positive to negative. That is electricity. And so that's how the body sends messages through our nerves, this nervous system, is this electricity, is this exchange of charges. When we look at charges, we're going to look at magnetism stuff a little. We look at the fact that positives push away from each other, negative and positives, or negatives also, but then a negative and a positive, the opposite, attract each other. So like when you put a magnet on the fridge, if it doesn't stick, you put the positive to the positive. If it flips it around, it sticks. You know you got the opposite, and then it repels it. Ions do the same thing. Physiological concept that we need to understand is opposites attract. All right? The positive and the negative are the opposite. If we have areas or fields of positive or negative charges, ions will tend to move towards the opposite charged field. Actually, what I do, I want to move away from that slide and I want to go to the next slide here. Because what that slide talks about, in order for having fields that are charged, let's say the inside here, we established that the inside here is more positive, right here, the outside more negative. Here is you have all these different ones, but all together, that's a little bit more positive, that's a little bit more negative. No, that's the other way around. Well, anyway, it actually doesn't matter. We're going to get to what's the inside, what's the outside over here. Because what I want to get to is the fact that we need a boundary to be able to establish levels of more positivity and more negativity. And that boundary in a wire, in a wall, where the electricity goes through the wall, that's the plastic. If you don't have it, it snaps you feel it. If you just don't touch the wire, if there's no plastic around. So that plastic is an insulator. In us, it's plasma membrane. That's like a plastic. That's a fat layer around things. So it's perfect. The wire, the axon, that long extension is a wire, and around it we have that fat layer that separates the ions from the inside and the outside. They cannot penetrate. Water cannot go through fat. So the hydrophobic layer lets the hydrophilic ions be either on the inside or on the outside. And so now what we're going to do, we're going to establish and establish a chemical gradient. So now we're going to take these different ions. Now remember, every ion has a charge on it. The charge is either positive or negative. But the chemicals are very different chemicals. They can be sodium, they can be potassium, it can be chloride, it can be calcium. K is potassium. And the ones we're going to look here is potassium and sodium. So when we look at the inside of the cell, or the inside of that tube, that long extension, right here on the inside, we have a lot of potassiums right there on the intracellular side. Intra means inside. In the cell. On the outside, down here it says extra, that's the outside. We have a much greater concentration of sodium. Na is sodium. K is potassium, Na is sodium. Now you see, they both have a positive on it. Alright, so that's going to be a little bit difficult, confusing. So that's why I want to make the difference right here between the charge and the chemical. So there's a difference between the charge and the chemical. The charge carries the electricity down the wire. The chemical having the charge on it makes that possible, moves the charge around. So you always have to have a chemical that moves the charge around. So looking at this picture, you see this is the cell membrane. So now here, the outside is a little more positive, the inside is a little bit more negative. If we take, so the electrical driving force is, you want to go to the inside. That would be the electrical driving force, right? You want to go from the positive to, if you are a positive molecule, you want to go into the negative side. But when you look at the chemical perspective, like who carries the charge, that's the chemical, you have more potassium here on the inside than on the outside. So the chemical driving force is going to be, to even that out, is going to be going to the to where there's less in it, right? So in this picture, if you open, you have a lot of potassium on the inside, very little potassium on the outside. If you open the channels that let potassium move across that boundary, potassium wants to go where there is less of them, so it balances out the chemical. With that chemical, it pulls a charge with it, and that is then the electricity. So boundary maintains different charged fields. The plastic around the wire is an insulator. The plasma membrane is that membrane that does that in the body, and it establishes an electrochemical boundary. So the boundary is for electricity, for the charges, the pluses and the minuses, and the chemicals, the sodiums and potassiums. Ions are hydrophilic and unable to cross the hydrophobic middle of the cell membrane unless a channel or a pump is present. Remember when we talked about channels in the cell membranes? In the cell chapter, the movements? This is what we're talking about. So these are channels that are specific to one chemical. So we have some channels here that we're going to have of interest in this nerve impulse. The potassium channels are very interesting for us. The sodium channels are also very interesting for us. They do not let a calcium through. That's a different channel. And then we also briefly talked about pumps. So channels we use, go back to channels. Channels we use to passively let, when they're open, passively the potassium goes from one side to the other, depending on where there is less or off. That's a passive movement. We just have the channel open or closed. Then we talked about pumps. And the pumps we talked briefly about in the cell chapter, they were active. They use ATP. They pump ions from one side of the cell membrane to the other side of the cell membrane. So we have pumps. This is a sodium calcium, but we also have a lot that we are going to talk about is sodium potassium pumps. So they use ATP. And what we learn about ATP, when ATP is used in cellular movement, it's across the cell membrane, it's moving against the concentration gradient. So those pumps can be used to push all the sodium, here is to the inside, but when we look at this, so we can push all sodium to one side, and we can push all potassium to the other side, and we can establish this sort of gradient, that there's a lot of potassium on one side of the cell, on the inside, and a lot of sodium on the other side. Because we push it actively to those sides. And then, if we open a channel that is passive, it will all flow out real fast. And we also talked about that in the movement across the cell membrane, that active processes use ATP, but they're slower. Passive processes can be much, much faster. So if we establish that tons and tons and tons of potassium is right here, right by this channel, and none is right out here, as soon as we open that channel, all of those want to flow out. It's kind of like, did you ever take the subway in Tokyo? Where they push people in, and they close the doors, and they squeeze them in like sardines? And so you got all these people squeezed in. As soon as you open those doors, those people all fall out. You got to be careful not to get trampled down. But that's kind of the same sort of situation. It's just we can have that for every chemical. We might not see it, but it can be for, it's chemical specific. Potassium a chloride, sodium, calcium. We going to be focused on the potassium and the sodium in this chapter. All right, so that's good for that. So we got the pumps out of the way, and we got the channels out of the way. And we understand that we move the chemical to change, to move the electrical part, to move the ions, which is the positive and the negative. And then the next thing we need to establish is the understanding that the change that we talked about, from one to the other, like this change here, from a negative on the inside all of a sudden to a positive on the inside, that change in the electricity, that's called voltage. So voltage is a change, or also really a difference between one side and the other side. So the fact that we call this positive on the outside and negative on the inside, that's because we measure it. And the measuring, the difference of that, that's voltage. And so, because just we need to just have the language for it. And so when we have a cell that's just sitting there, that's not firing, like, you know, I'm not moving my leg around too much, or when I do, then they fire. When I don't do, they don't fire. When they don't fire, the pumps make sure the inside here is a little bit more negative, and the outside here is a little bit more positive. The outside has much more sodium on it, and the inside has much more potassium on it. That we want to know that. That's at a situation where we don't do anything. So when we just sitting there at rest, the outside has a lot more sodium, and the inside has a lot more potassium from the chemical side. And you go like, well, how is that going to make a difference with the electricity? The reason why the electricity is a bit goofy and doesn't sometimes make sense with the positive and the negatives is the fact that we have a lot of these anions. These are anions. And anions are large molecules that have a negative charge, and they're overpowering the fact that the inside, generally speaking, is more negative. So it's these anions that make sure this inside is, generally speaking, more negative. But what we're going to be able to do when we have an area that we open these pumps and let all that sodium come in, we let all that positive come in, slowly, briefly, at that state, that place, it reverses. And the anions don't overpower because we let so many sodiums come in. And then that is when that happens. And then that's the electricity, right? The switch, changing the ions creates that electricity. And so, right here, that's a nerve impulse, right here. And we use the word depolarization to describe that part of the process. Because the word de means less of something. Polarization talks to the fact that when a nerve is at rest, that's at rest, it does not move, right here, nothing goes wrong, but we have that difference between the negative and the positive on the inside and the outside. That's polar, like the Earth, North Pole, South Pole, or like the battery in this microphone, a positive and a negative, that's the pole. Polarity. So when we change that polarity, we take that polarity away, we call that depolarization. We flip it. So that's the voltage situations, the charge difference between two fields. And it's changing when we have a nerve impulse. But to establish that resting situation, we have to have what I said before, these pumps that make sure they continuously, all the time, pump sodiums to the inside, potassiums to the inside and sodium to the outside. That's the outside, that's the inside. And when we measure right here right at the cell membrane level, not the whole inside, just right there at the cell membrane, that difference is about 70 millivolts. Actually, negative 70 millivolts. More negative on the inside than the outside. And we call that the resting membrane potential, RMP. And that's the same as this is described here, okay? So that's that state when we are at rest. We have it is a polarized state. And then from there, when we have that resting membrane potential established, then we can open gates. When we want to fire a nerve impulse, we can open gates that let sodiums, since sodium is in the outside, more highly concentrated, we open the gates, the sodium come all rushing in, bringing that little positive charge with it. And that changes the voltage, making the inside a little bit more positive as it was before. They call that depolarization. So it's not 70, it's now only 20. It's not that big of a gap anymore. And then it flips, it goes into the positive. And then now we have a cell that has fired. The electricity has shifted. The inside is now more positive briefly. Now what we gotta do is we gotta flip it back to stop the nerve impulse. The nerve impulse is a shooting, is a quick spike, but then the electricity changes right back to make the inside back to being more negative on the inside here. And we established that, well, how we established that by using a different chemical and move that different chemical from the inside to the outside. Because the sodium is now all evened out. We're not going to be able to move more sodium back out. We have to use the pump for that. But now we have this other chemical, the potassium, that is kept at a higher concentration on the inside, intracellularly. And when we open carriers, or channels, that protein channels that let the potassium go, potassium wants to move out. The chemical wants to go out, and it's going to carry that positive charge back out, making the inside more negative again. So you're flipping that positive to negative and negative back to positive, depending on how you're looking. And you're doing that function of changing the the voltage by moving the chemicals. And together, we call that an electrochemical event. So a nerve impulse is an electrochemical event because we use to move the chemicals to change the electricity. And when I done that potassium and all that positive is back out, and so we're all back all nicely like in the beginning, the negative is inside, the positive is outside. That process is called repolarization. We reestablish that original state. And now we're back to this, except the chemicals are screwed up. And slowly the sodium potassium pump makes the chemicals back that they're unscrambled, and it all goes back to this, and then we can fire a new nerve impulse. What that is doing, what's good about that is we have a brief intermission between firing again. We have a brief moment in a nerve sequential firing that it cannot fire. So that makes the loop be complete. Because we're going to use that, because every time we fire, this is not gradated. This is all just fire, non-fire, fire, non-fire. And so a nerve cannot sort of, tell the brain how loud something is, for example. It has to, grade it differently. It cannot just say, oh, let's fire a little bit less. It's just on or off. And it does that grading, that firing louder or less loud by frequency of firing. And so having that loop be closed by having these chemicals have some time when these need to be reestablished, then we can fire an impulse again. That gives us the ability to frequency stimulate and code. It's all like electricity. It's all like Morse coding type stuff. If you think of how the nervous system talks, when you actually make this nerve impulse so you can hear them, it's like Morse coding. It's that kind of sound. So it's an electrochemical event. All right, you kind of got that? Yeah? Good. Let's hope this works. So then that is basically what I described to you is the action potential, is the nerve impulse. So let's just talk about it in the terminology that we, let's see where we have that. Yeah, let's talk about it in this terminology, because that's what we just did. Now it just looks a little bit more official. Mechanism of an action potential. So the first thing that happens in a nerve impulse, here's a nerve impulse. This is at rest right here. So nothing happened yet. But then we say we gotta fire that nerve. When we decide that we gotta fire that nerve. And we're gonna go back to what does that mean when we decide. But at that point, the sodium channels open and the sodium rushes into the cell. Into the cell, and the electricity here, that's the voltage. This is the voltage here. The change in electricity. It spikes up from negative to a little bit of positive. See that? 30 millivolts from negative 70 to positive 30. So that's when we flip the inside gets into the positive now. And then at that point, somewhere here, we're gonna close the sodium channels because we've done enough of that. And then voltage gated potassium channels. That means the change in voltage opens those potassium channels automatically, and then potassium flows from the inside of the cell to the outside, carrying that positive charge, dropping that intracellular voltage down below actually negative 70. And that's because those channels are slow to close, they say. And so it's almost like we hyperpolarize. So we depolarize, we repolarize, and then we hyperpolarize. And then it slowly evens itself out with the sodium-potassium pump. And at that point, we can fire again a new stimulus. So again, here, sodium channels open, sodium enters the cell, changing the voltage to about positive 20 millivolts. That's depolarization. That's number 2 here. Sodium channels then close, stopping the influx, that's number 3. And then potassium channels open, potassium exits the cell, restoring the negative voltage. That's number 4 in repolarization. And then sodium potassium pumps restore the chemical environment, and that's here number 5. So I like that graph. When I found it, I was happy. Because that pretty much summarizes it. And so then we still have one question left right now. The question is, when do we fire one of those puppies? When do we fire a nerve impulse, an action potential? And then now let's go back to the cell, the nerve cell, the neuron. That's that long extension, and we called that the axon. We might as well learn it now. And then right between the body and the axon, there is a place called the Axon Hillock. And at that place, the neuron makes a decision, do I fire or do I not fire an impulse? Because when you look at the other side of the body, all these extensions here that come out, they branch out all over the place, and they have other nerves that talk to them. Up to 1,000 of other nerves talk to them. And they all gonna basically tell this neuron 2 things. Fire or don't fire. Excitatory impulses or inhibitory impulses. And then these impulses, they're like, you know when you throw a rock into a body of water that's silent and it ripples off, the ripple thing? It's like it ripples off, and it's like echoing through the cell body. Oh, we should fire, we should fire, we should fire. There's a voice. You got 1,000 voices saying, should we fire, should we not fire? And depending on how loud or what the voltage change is, basically, that's the language the nerves use. The message is right here at the Axon Hillock. If it drops to a threshold level, negative 50-ish, it says we're going to fire. And at that point, it decides that, and then this happens. And once this happens, you can't stop it. Only if you break the nerve in the middle, but that's really difficult to do. Those nerves are fast. So then a nerve impulse is known as an all or none phenomenon. All or none. An action potential. And we separate the nerve impulse, that's that all or none, that action potential, from the graded or local potentials, and those are described here, what I just wrote on the other side. All these that come into the nerve and say, oh, let's not fire, let's inhibit. Or let's fire, let's excite. And then whatever the summation of that is here at the Axon Hillock decides if the nerve gets fired or not. Look at that. Threshold, sorry. The threshold here is about negative 55 millimoles. If that change in voltage from negative 70 to negative 55 happens here, it's firing. And then this happens. And this is a little description of all these little voltage changes, and then all of a sudden you get that summation and it goes. The trigger's taken and it shoots. All right, so that's good. Action potentials are all or none. So they do go or not go. They're all equal form, equal intensity, and equal duration. They're not graded at all. So they do not tell us, is a voice loud or soft? Is a light bright or darkerish? Or any of that. Neurons use frequency to code the intensity of an impulse. And this is possible because action potentials are very brief in duration. So they can do that. They do that this way. So this is just kind of like, you know, a force of contraction in a muscle here. A little twitch is one action potential. A little stronger twitch that summates, that gets stronger as it contracts, is two. And so on and so on and so on. So if you have to step up all the way, it continuously fires that all the muscles are firing as much as we can. Action potentials move along axons unidirectionally because localized change in voltage opens neighboring voltage-gated ion channels. So what that means, and there's a couple of reasons. What that means, an action potential can only go one way, cannot go the other way. So it only fires out one direction. Because you cannot go back, because back here where you came from, all the chemicals are scrambled. So it's not going to be working. That's what I meant with that. The having to reestablish the chemical mixture with the sodium potassium pump. That's good. And then we have a couple of tricks in the speed of the action potential going down a nerve. We have very varied in speeds. We have a few meters per second, or we get up to 120 meters per second. So that's a lot. A meter is this much. To 120 of these a second, that's how fast it goes. Or only a couple. Of course, the pain fibers go slow, right? They have to constantly nag us. So that's the slow stuff. The stuff that is like reaction times and all that, that's the fast stuff. The transmission difference speed is mainly caused by how large an axon is, like how the diameter, how big it is, but also by is it insulated by myelin or not. And myelin sheath is a phospholipid envelope that surrounds the axon, and it prevents ion exchange. So now you got like this regular insulator here, that's the cell membrane, and you take, actually it's another cell, it's called a Schwann cell, and you wrap stuff around it and make an envelope of more fat and just make sure no ions can go in and out. There's no channels in that one, only in the first one. But what you do, you have areas in between these wrappings that are left blank, and in those places the ions can exchange. And so now the action potential has to like chomp because the ions exchange here, so voltage changes here, and then it has to go all the way up to here, where those channels have to pick up the change from over here and open. And that chomp speeds up the transmission, and we call that saltatory conduction. Saltatory, a chomping nerve impulse. And the areas that are left blank where the ions can easily go in and out, those are known as nodes of Ranvier. Just so you know for the future. Make sure, this is physiology stuff, so make sure when it comes to studying this, you go to the test review. Don't study the whole, study the whole thing, that's great, but don't overwhelm yourself. Try to understand the whole thing, and then from a test recall perspective, go with the test review. And make sure that stuff you understand, and come talk to me or talk to your neighbor, student, people, and get feedback on those things. Because those are the things that are on the test. And there's not everything on the test, because it's a lot of material. All right, so that's good. So did you understand that nerve impulse more or less? Are there any questions that just come up right now? No? Can we go home yet? No.